And the screens are...
Okay, yeah, I'm going to move the video down here.
And just go with that little screen there. Probably going to have to be.
Yeah, well, that's as big as it's going to be.
Oh, that's fine.
Yeah.
I mean, can everybody see this? You okay with this? Okay. All right.
There's a little feedback going on here.
Yeah.
It's over here.
Oh.
Yours is on.
Yeah, you can keep it. Okay, yeah, well, go ahead.
Okay.
And we're all sorry for the delay.
Hello, and welcome to Popular STEM Talk 3 of Spring 2014. I'm Stephan Fitzpatrick. I'm a geology and environmental science instructor at Georgia Bruner College. And I'm going to talk about a project that I've been doing since 2008. It's the construction of soil core monoliths, okay? I'm going to explain what the heck these things are, because kind of an obscure application. It's actually, this talk is going to cover the basis for soil science, if you're interested, and it's also going to discuss a little shop project. Okay, so. Okay.
Yeah, like low, I think.
Oh.
There's a lot
Okay. You got the technology going.
Yeah.
Okay. What is a soil core monolith? Well, it's a method for preserving soil cores at in situ conditions. Now, in situ is Latin for in position, or the original state. So if something's in situ, if you go out there, you find a rock outcrop, as it is, that's in situ, okay? And you use these for display, instruction, transport. You can study them. You can study soil structure. These are a lot like what biologists do when they get skeletons and skins of animals, and they put them in museums, or they assemble them as sort of the original condition of the animal to study and to sort of use as a museum piece. And these certainly are museum pieces, as you'll see. Okay.
Yeah, when that image is, and then takes a little long load.
Gonna have it.
There we go.
Okay. What's a soil core? What's a soil profile? Okay, a soil core is a vertical sampling of a soil profile. A soil profile is the entire vertical sort of length of a series of soil horizons. Okay? Soil forms because of very distinct conditions, due to very distinct properties, conditions and properties, vice versa. And this is how you get horizonation. This is how soil undergoes horizonation. A soil horizon is a unique or a lateral segment of the soil that has very distinct properties. Okay? And they're placed because of natural processes such as drainage or compaction. Okay, soil horizons start at the top with the designation O. You don't find an O horizon in a lot of soil profiles. Okay, remember, soil horizons are lateral because it's a lot like Steno's laws in geology. A lot of the basic sedimentological laws in geology. Okay, once something falls down and becomes some sort of sediment, the next layer is going to be the younger layer because it's the law of original horizontality, just like in geology. Well, this can be applied to that to a certain extent. An O horizon is an organic horizon. Okay, they don't always accumulate. Our soil out there, the Northeast Georgia Piedmont, doesn't have a whole lot of O horizons, but we've got a lot of A horizons. A horizon is an intermixed organic and mineralogical horizon. Mineralogy being the basis, being the rock that's been weathered, broken up. Beneath that, you may have an E horizon. E is where drainage accelerates. And where drainage accelerates, water, being the transport mechanism for our planet, picks up dissolved constituents and ions, carries them down. We actually don't have that. You go to South Georgia, you might find some of these. E horizon. Beneath that is the B horizon. The B horizon is very special. We'll talk about that in a little bit. The B horizon is where clays and iron and calcium accumulates. Beneath that, you have a C horizon. C is the weathered bedrock. It's in situ, it's in place, but it's been weathered out. Okay? It contains a lot of pore space. Around here, the C horizon is going to contain your water table. It's going to contain your groundwater. Beneath that, you have the R horizon. R horizon just designates rock, bedrock. Wow, that was fast. Okay, there are 5 soil formation factors. You do not have a soil if one of these is missing. There's parent material, climate, topography, time, and biology. Okay? Parent material is the rock. The rock becomes broken up, becomes sediment. That's how things work on the surface of the earth. That's how things work on planets, by the way. Okay? Climate is the action of wind and weather. Okay? Climate is the movement of the air. It's the movement of the water. It's the movement of fluids in the atmosphere, affecting both the lithosphere, the biosphere, and the hydrosphere. Okay? Life, rock, water. Okay? Topography is basically your slope. You got a cliff, can't really have soil on it, can you? But in the lowlands of Mississippi, you'll have very thick soil profiles. Biology is integral to soil. Okay? Living things deposit their matter. Worms deposit their castings. That becomes part of the sort of the nutrition of the soil. This enables plant life to grow. Plant life is extremely important for existence on Earth, existence on the surface of the Earth. And then there's time. Soil profile, soil takes a lot of time to develop. The ultrasol that we have out there, right outside, took several thousand years to develop. Okay. That's back to its old tricks. Yeah, there must be, it's the images. I'm glad I didn't put too many bells and whistles on here. Dancing dog. Okay, 12 soil orders. There are 12 overarching orders to soil taxonomic classification. And you can, and you do, classify soil just like you do animals. Okay, there are 3 domains of life: eukarya, prokarya, and the archaea. Okay, so there are 12 soil orders. Okay, they vary from gelisols, which occur in permafrost soil, to oxasols, which are tropical soils that you find near the equator. There's our soil, which is the ultrasol. You're going to hear way more than you ever wanted to hear about ultrasol really soon. And then, of course, you can map it. This is a map of all the soil orders. Traverse the world and look for soil orders. Ah, there you go. Soil monoliths, again, a way to preserve a soil profile in situ conditions to analyze the soil horizonation, the soil, even the soil chemistry, the drainage characteristics, and the appearance. Okay, these were first collected in Russia in the 19th century. Folks from Russia were some of the first soil scientists on Earth. Okay, and they were originally preserved in wooden boxes. Okay, and they were just sort of laid down horizontally. But in order to pick them up and put them on a wall, people started experimenting with different binding agents. Sugar was one of the first binding agents. Okay, when you introduce a binding agent, it's called impregnation. Okay. Yeah. Words are disappearing. That's okay. Okay. So later on in the 20th century, people started experimenting with PVC and solutions of PVC and alcohol and acetone and other chemicals. Okay. Latex, other polymers, because when you have polymers, you have long chain molecules, and once they go out of solution, they tend to, it's like plastics, they tend to adhere to what they're part of. Another popular method is lacquer peel. That's okay. Lacquer peel is literally where you have some sort of glue and you put it on the face of your soil pit. People who study soils create big pits that they can get down into and see the soil. And using the lacquer peel method, you can press it to the soil, peel it back, and then you'll get a nice representative. I think we have one of the best methods. I'm willing to bank on our method. You'll find out about it in a minute. It's a good product. Okay. So our soil that we did our experiment on came from paddock number 6 at the USDA ARS, Agricultural Research Facility in Watkinsville back in 2006, October 11th of 2006. And so this is a humid temperate climate. Unfortunately, the cores sat around for about 2 years before they were given to me. So there are a few problems with that, and we'll talk about that later. But this is where they came from, Watkinsville, Georgia. Yeah. See it. Another big. Ah, there you go. It is a big graphic. Big graphic. Okay. So, yeah, big guy. Okay. So, soil core, okay, it originated as part of the Athens gneiss. If you take in geology, you know that gneiss is a metamorphic rock. Gneiss is a metamorphic rock that contains a lot of feldspar. Okay, feldspar, about 50% of all Earth materials, rocks in the Earth's continental crust are feldspar. Plagioclase feldspar is the most common mineral on Earth. Okay, it weathers to a clay. It weathers to a clay called kaolin. Okay, so in gneiss, because it's got a granitic composition, you have a few iron-bearing minerals like biotite, you have feldspar, and you might have some other minor constituents. Of course, the biotite will chemically weather out and turn into iron oxide, hematite, rust. Okay, so this core that we got with the parrot rock gneiss is an ultrasol. We'll explain that in a minute. This graphic. It's grinding away. Oh, that's a small graphic. Okay. Ultrasol. What do I mean by ultrasol? Well, an ultrasol is one of the 12 soil orders. Remember I was talking about the 12 soil orders that you can map all over the earth? Well, ultrasol is one of them. Ultrasols they occur in temperate, humid settings. We have a humid, temperate setting, don't we? Okay, it rains a lot. It's not always that cold. It gets really hot in summer. The drainage is okay. Well, you end up with this. Ultrasols have a rich B horizon. B horizons are clay rich. Tends to be very thick. Ultrasols also have a pH that is below 7. They're acidic. That's why pine trees grow so well here in Georgia, because pine trees don't mind an acidic soil. But if you're going to grow, let's say if you wanted to take some artichokes from California and grow them here, you'd have to add a lot of lime, or a lot of what we call limestone-derived products, calcite. They're very basic. They have a high pH. You have to titrate your soil, basically, and drive that pH up past a point, the titration point, okay? Texture, grain size is another important characteristic of soil. Ultrasols contain a lot of clay, especially in the B horizon. Clay is a nanoparticle, tiny particles that are formed like plates. They stick together like glue, and they impede drainage. When you impede drainage, you end up with problems, of course. You hold water up. Clays will absorb lots of water, but they won't let the water pass through. Like a sponge that won't transmit the water. Okay. And of course, that clay is kaolin, the billion dollar clay from Middle Georgia. You go down to Sandersville, walk around, get yourself a nice milkshake to the dairy lane, walk around and actually see white powder. And that powder is the kaolin that they mine. Okay, here's our material. This is what we gathered together. Okay, mostly what I gathered together. But so to start with, you have the 9 soil cores. 9 segments of a 13.02, a 13 200 meter soil core that was taken from Watsonville, Georgia. Okay, divided 9 ways. Okay, so it's going to have 9 soil cores, 9 monoliths. Okay, I had to get some polyvinylidene chloride because on suggestion of my partner, my colleague, Dr. Paul Schroeder of the UGA Geology Department, we were going to work with polyvinylidene chloride. We talked about it, and because it's a component of saran wrap, it seemed like a good polymer to use. So I ended up having to order it from France. They don't sell it in small amounts here in this country because guess what else polyvinylidene chloride is? It's volatile. It's used in firecrackers. It'll actually explode. So it's also, you don't want to breathe. So I got some of this resin from France, from the Solvay Corporation of France. And later on I got some from USDA in Nebraska, but we'll get into that later. I had several reagent bottles. If you've taken chemistry, you know what a reagent bottle is. Okay? I had over 3 liters of laboratory-grade acetone that I used. I needed a lot of acetone. I got some wooden boards, some carpentry tools, a large gardening pail, some polyurethane, sort of a lot of carpentry supplies, and I went to work. There's my workshop. That's the blockhouse over at UGA. The soil science professor, Dr. Bill Miller, he has a place called the blockhouse. It's a wreck, but it's a good place to do soil work. Okay, so our procedure, how did we do this? Well, we deliberated. Dr. Schroeder, who's basically a geochemist, knew some really good procedures how to go about doing this. You do ratios of mixtures, you test them out. I had some smaller cores that I tested out my ratios on. It came up with a 5-to-1 solution, okay? 5 parts acetone to 1 part, by weight, mind you, PVDC. Mix it up, try to make it homogeneous a solution as I could, and tested it, and it worked. Okay. Next, we built some wooden boxes, and I had the help of GPC physics and astronomy professor Fred Bowles, because he's an expert woodworker. We got together and built wooden boxes that would fit the cores. Okay. They were measured. Everything was carefully done, and then we put the cores in. Did I have? Yeah. We put the cores in the boxes, deposited the boxes, made sure that we flipped them correctly. Then I used a hammer and some brushes to brush the soil out flat, okay? And the thing is, I had to do it laterally because I didn't want to disturb much of the horizonation. It took a lot of time and effort because, yeah, there's a little bit of art to it, but you need the science in there too. And if you completely ruin your horizonation, which is the direction of drainage, it's the direction of the deposition of and the activation of all of the chemicals and the grains and textures, you're going to end up with a product that doesn't make any sense. So it took a while, managed to do that, and then when it was done, I cleaned it up. I took the PVDC acetone mixture, used a metal gardening pail to impregnate the cores. They dried really quickly. Acetone evaporated in anywhere from 30 minutes to an hour. And what was left was sort of an artificial sedimentary rock. Really neat. Then I took polyurethane, once it was dried, clear polyurethane, coated it to preserve it, and took a little wood stain, dressed up the wood, and they were done. Let's talk about acetone evaporation. Okay, well, when liquids are placed in an open container, they tend to change from a liquid to gaseous state, okay? Because liquids, both liquids and gases, and you call liquids and gases fluids. A liquid and a gas are both fluids. They're fluid, okay? They take the shape of their container, okay? Well, the atoms and molecules exhibit kinetic energy, and they escape. Water evaporates, okay? Acetone evaporates at an even greater rate because it has a lot of kinetic energy, okay? And according to the gas pressure laws, Le Chatelier's principle and all that, when you have a gas that's contained, that's sealed, and you take the seal off, the mixture, the gas, the entire system wants to go back into equilibrium as far as pressure is concerned. And because of that, and the kinetic energy of the molecules and atoms, it'll escape and evaporate. Acetone is so active that it takes hardly any time for the stuff to evaporate. Evaporated in 30 minutes to an hour. What was left behind were the particles that were bound with the PVDC, and it actually turned out pretty well. I also took a sample from 93 centimeters down of the soil, and I ran it through an X-ray diffractometer. X-ray diffraction, or XRD, is a method used to determine the composition of crystalline substances. Okay, they have to have a crystal orientation. They have to be composed of crystals. And of course, minerals are composed of crystals. By definition, an earth material mineral is composed of crystals. If it's not crystalline in structure, it is not a mineral. Clays are minerals. They're tiny minerals. They're tiny minerals that don't grow. They remain as individual little platelets that tend to aggregate. That's why clay stones are the most predominant. Anything derived from clay is the most predominant type of sedimentary rock on the Earth's crust, because there's a lot of it out there. About 14% of the Earth's surface is covered in clay. Okay, so we used XRD. They had a great new XRD at University of Georgia. If you go into the University of Georgia and taking geology, they have, oh man, it's a beautiful machine. We took it for a test drive and everything. Okay, so you send the X-rays through high energy electromagnetic signals, basically, and the what happens is the X-rays are scattered. They're diffracted. And the pattern of diffraction and the intensity of diffraction is read in that kind of chart right there. And each type of mineral and or element has its own unique place and often its own unique intensity. Okay. Using that, we determined there was a lot of quartz there. Sure. There's a lot of quartz out there everywhere, okay, in the type of soil that we have, but there's a lot of kaolin too, kaolinite. And so one of these intensities is kaolinite too. We determined, okay, it's kaolinite. You know, it's kind of neat to do this with an XRD. And I learned a lot. I learned how to use an XRD, so it was fun. It's an interesting instrument. Okay, and there's the end product. There they are, 9 of them, on permanent display at the University of Georgia's Geology Department, 3rd floor, bolted to the wall, 9 soil core monoliths. Starting with number 1, that's the topmost soil, on down, and that's the very bottom of the core. When it was originally extracted, that was at the bottom of the drill. Close the door here. But it turned out really well. They're very solid, very durable. These things will last possibly hundreds of years. There were some problems, though. Okay. Ooh, observations and conclusions. Okay. Well, that's okay. I remember. A fairly large amount of the acetone PBTC solution ran out the bottom of our boxes. okay? So, next time when I do this, and if you ever want to do it, keep in mind, have a liner, get a plastic liner, line the bottom of your box with it to prevent a lot of that stuff from, and it's wood, so it's, you know, it's wood that was joined together with wood glue and with nails. So there's going to be lots of cracks, lots of openings, okay? The core that we used for the project has been stored for 2 years. That was kind of to me, that was the biggest problem. The idea here is you extract the core and you preserve it almost immediately. You're getting a true in situ representation of the core itself. But these were, well, I was in undergraduate school, okay? But these sat around for 2 years before I got a hold of them. They accumulated dust. They absorbed moisture. They weren't really what they originally were. And that's the big problem. When you do this work, get your core, and as soon as you can, within a week, heck, within a day, start the process so you'll have a true representation of your soil, okay? Use a fan and wear a gas mask. I wore a gas mask because acetone is horrible. It's toxic. And PVDC is a fine resin powder. It tends to, any little draft that you have while you're working with it will pick it up. You don't want that stuff in your lungs, okay? So when you're doing this, you need to wear a gas mask. You need to have a fan going. You need a well-ventilated area, okay? Neatness counts. Because of the scope of the project, you're generally going to work with cores that can be anywhere from 2 to 13 or 14 meters in length. The scope of the project and the fact that you're doing what you're doing with the chemicals that you're working with, neatness really counts, okay? So be very neat. Other than that, I think we have a great method for creating soil core monoliths. I think this will work across the board. I mean, I'll stand behind my product here. This is our product. And, you know, not that we're going to get rich off of it, but, you know, I think it's a good product. Okay? Well, that's acknowledgements. Let's do some acknowledgements. Yeah. Okay, well, all these folks help. Dr. Paul Schroeder is my colleague on this. I should have added Dr. Dinku Ndale, but he just came on board. Dr. Ndale is a soil and water specialist, an agricultural scientist for the USDA in Oconee County, Clark County, that whole area. He's great. He's coming on board as one of our co-authors because there's a paper. We're writing a paper and we're going to publish it, possibly in Clay Minerals, possibly in the Journal of the Soil Science Society of America. Okay, so he came on board. Dr. Bill Miller, crop and soil scientist, who's a soil chemist, was a great help. He helped me determine what some of the specific horizons were in the soil, and exactly because each horizon has a different sub-designation. A B, that's also a T, a BT, is a clay-rich horizon. Okay, so you know. He was great. Stephen Norris is one of the technicians, is still one of the technicians at USDA, although they moved since to elsewhere. Fred Bowles, here on faculty at GPC, physics and astronomy. He helped me build the wooden boxes. Nathan, over at Mesa, a chemistry expert, helped me understand more about acetone and certain aspects of organic chemistry. So I thank him, the USDA Soil Survey Center in Lincoln, Nebraska, the Soil Museum in the Netherlands, the World Soil Museum, that's right, and Solvay Specialty Polymers, their headquarters in North America is Granville, Ohio. So I was able to get my resin that I needed to from them and from the USDA in Nebraska. Any questions, comments? Interested in a project?
I have a question. So these soil cores that you prepared, where are they going now?
They're going to stay there.
So they're on this place?
Yeah, the geology department, UGA.
And basically, so you came up with a method and technique that could then be used for other geology labs
Yes, exactly. Exactly what Enrique said. You're right. This method can be used to extract soil cores and turn them into monoliths just about anywhere. What I like about my method here, our method, is that it takes an entire core. Okay, the lacquer peel method that I mentioned is just kind of you kind of get sort of the surface. This you actually get a nice thick core segment, and you'll get a very nice representation of exactly what the soil is. Okay, it's like the difference between in another biology analogy, getting the head of a leopard versus the entire body on display in a museum. The entire body is much more representative of what the leopard really is, and you can study its external anatomy, the shape of its body, the volume and all that, and the way it appears in greater detail and to a greater extent if you have the entire leopard. Well, this method of, I guess, monolithizing a soil core, I think, is just better in a lot of ways than the lacquer peel method because you get the whole core. You don't get just the outer surface of the vertical section or component of a soil pit. So, it's fun, too.
What kind of experiments could you run with the soil core like that?
Well, you don't really run experiments. Once you have a museum piece, there's no real experimentation, but it's a teaching tool. And in a way, you can run experiments in determining the thickness of the horizons. You can do those measurements really easily. In fact, it's a lot easier to do it with something that's static than it is with something that's changing all the time. You could go to your soil pit, take some measurements, go back the next day, and there's been a rain, okay? And you're going to have a lot of drainage, you're going to have a lot of outwash, You might have something slightly different. This way, and it locks it in place forever, basically, unless somebody drops it. Which happened with one of them. One of the grad students. Leave it to a grad student. They dropped it, cracked it. That was sad. Any questions, comments?
Okay.
Well, thank you for coming out. Thank you.
I apologize again for the technical delays.
All part of being,
Sometimes in this room and,
part of being in the digital age. As you can see.
Everything.
That's right.
Okay.